Sumit Puri. Oh, I should. Okay, I'll start now. Next up are Platinum Sponsor Talks. And we have two talks. The first one is by Sumit Puri. He's a CEO, co-founder at LIQID. He's talking to us about Dell's MX7000 and LIQID Matrix. Hi, Sumit. You're ready to go?
Yeah, guys, absolutely. Thank you. Obviously, very difficult act to follow here, but thank you for the opportunity nonetheless. Wonderful to hear Andy's perspective on things. So, guys, I'm going to go ahead and share. I hope you are able to see my screen.
Yes, we
quick
are.
Screen check. Okay, great. So I'm going to kind of move quickly through this. I know I only have roughly 19 minutes left, and I will try to stay on time here. So what we're going to cover today is two parts. Number one, we're going to cover a little bit around the LIQID technology that enables something referred to as disaggregated composable infrastructure. And then we'll also explain the project and the partnership that we've engaged with Dell around bringing some disaggregated capabilities to their MX7000 platform. We'll explain a little bit on both sides. But with that, let me start a little bit on the market. This is, a slide that we like to show that talks about, the data center roadmap. Where are we going with data center architecture? Kind of where we are, where we've been, where we're going. The two key takeaways we like to express on this slide. Number one is that static infrastructure is dead. Statically configurable infrastructure is not the future. Our belief is dynamic infrastructure is where we are headed with data center architecture. And two fundamental technologies will enable what we call this dynamic data center. One of them is the concept of hardware disaggregation. And then the other one is the concept of software composability built upon pools of disaggregated hardware. The term the industry is using for this is called composable infrastructure. A little bit on how we define composable. Normally what we do is we take devices and we plug them into the sockets of the motherboard, and that's how we define what our machine or our server looks like. In a disaggregated world, we take a slightly different approach. What we do is we take pools of resources, pools of just storage, pools of compute. These days, a lot of pools of GPUs, networking cards, FPGAs. It doesn't matter what the physical device is. Instead of taking that device and plugging it directly into the sockets of the motherboard, we take trays of these devices and we plug them into a switch. It could be an Ethernet switch, it could be an InfiniBand switch. These days, we do a lot of PCIe switching. The software works the same. Number one, inventory all the different pieces of hardware that are available. And then number two, compose your server from these disaggregated pools of hardware at the bare metal. Grab me this one U pizza box, grab me 6 of those storage things, grab me 12 of those GPU things, interconnect them at the bare metal, just like we were putting devices into the sockets of the motherboard, except we define it in software. And on the other side, we get delivered server infrastructure, however big or small we want that server to be, except that server is dynamically reconfigurable. So when my AI workload needs another NVIDIA GPU, we don't send a human to the data center with a screwdriver to pop open the hood. We simply reprogram the switch and we add or remove devices from the server depending on what the user or the application layer is looking to do. One of the big uses for us is really around cloud. We work, for example, with a lot of transportation companies. If you think about a transportation workload, what's happening at 5 p.m. looks very different than what's happening at 2 o'clock in the morning. And a lot of times our customers are playing this game of workload matching. Small workload, small server, the world is good. Small workload, big server, we're actually throwing away infrastructure and we're not getting maximum utilization out of that hardware. We take a slightly different approach where we study the workload on the inbound. We dynamically spin up our t-shirt size, small, medium, large, however big we need that server to be. And when we're done with that workload or when the workload change, we don't sit there with underutilized hardware. We hit the delete button and we, for example, free that $10,000 NVIDIA A100 GPU back out into the free pool of resources. So some other application, some other server, some other user in the data center can get more utilization rate out of that very expensive hardware that we're deploying. And for a lot of our customers, it's not a question of, do I want dynamically configurable stuff or do I want statically configurable stuff? For a lot of our customers, it's a very simple question. Am I going to own infrastructure? Am I going to give all of my dollars to public cloud, or am I going to actually own infrastructure on-prem or in a colo? And what this concept of software defined and composable infrastructure delivers to a lot of our end users is the ability to have that cloud-like consumption model of hardware, 4 clicks of a mouse and give me a machine that's this big, and when I'm done with it, make it somebody else's problem. We give that capability to customers who want to own infrastructure on-prem or in a cloud, and we actually can save them a tremendous amount of money versus deploying some of these very high value workloads like AI in public cloud. So that at the end of the day is our kind of mission, to make all infrastructure dynamically configurable, similar to what we would receive on public cloud. One super easy to understand use case for us is really around media and entertainment. We have a customer in SoCal who's in the media and entertainment space, and they're also leveraging GPUs for different workloads. They have a workflow where during the day, they are able to compose this pool of GPUs to their AI engineers. And when they go home at night, they're able to actually set a policy in place that says, when these guys go home at night, automatically reprogram the fabric, move those physical devices to a different set of servers. For the next 8 hours, I'm going to use that same piece of hardware for video rendering. Basically take $50,000 worth of hardware, double the utilization of it, because I'm able to make it composable, dynamic, and move those resources around to the point and to the servers that can best utilize them. A lot of what we do here at LIQID, our #1 use case, is actually around artificial intelligence and AI-centric workloads, whether that's machine learning, deep learning, inference, high performance storage. But I think the interesting thing that we like to talk about related to artificial intelligence is AI is not an event. We don't go do AI, right? That's a kind of misinformed statement, right? AI, like many other things, is a workflow. That workflow normally starts with things like data ingest, right? We're bringing the data into the environment, and that's a network intensive thing. And then we talk about the tagging, the cleaning, the scrubbing, the preparation of that data, and that actually tends to be a CPU intensive thing. And then we move on to the training of the data, right? The machine learning, the deep learning. These are the big GPUs, the A100s, the V100s, 4 of them, 8 of them, 16 of them, 20 of them, as many as we can use connected to a single compute node so that we can do our training algorithms faster. And then we move on to data inference, which is the practical implementation of what we learned during the training process, but yet that's a completely different hardware profile. And at the center of this whole thing sits massive amounts of data, petabytes of data in certain cases. And the old way is these are 4 different servers, and we're shuffling data across 4 different servers on a network link, right? On a network link. In a disaggregated composable world, we take a slightly different approach to this. We put the data at the center of the universe. And when we need to do our data ingest thing, let's bring in the networking. When we need to do our compute thing, let's bring in the compute. When we need to do the training, let's bring in the big GPUs. And when we don't need those physical resources anymore, let's free them back out and let somebody else have that hardware. So here's an example, since we're doing this presentation in partnership with Dell, of a bundle that we've built with the Dell team to specifically go off and address some of these AI-centric workflows. So in this example, we have just 4 standard Dell servers. These are standard 1RU Dell R640 servers, but instead of putting the GPUs, the networking devices, the storage devices in the servers, we put those devices inside of these expansion pools. And so when compute #1 needs to do his data ingest thing, no problem. Let's compose some networking cards to that compute and give him additional networking capability. When compute #3 needs to do his machine learning thing, great. Let's go grab 4 of the expensive GPUs and compose them over to that compute node. And when he's done with them, we can repurpose those for another one of these compute elements inside the stack. So these are the kinds of solutions that we are building to go off and address these problems around AI with this disaggregated architecture that we're going off and implementing. And I only share this slide because the very question we get asked many times is, well, as you disaggregate, aren't there performance penalties? Things must run slower. And we show this slide to kind of show you, depending on how you disaggregate, for example, if we disaggregate over the interconnect of PCIe, we can actually deliver solutions that have a 1U server connected to 20 GPU devices, and we're able to maintain the levels of performance as if all of these devices were directly inside of that physical server. Again, goes to show the power of being able to disaggregate the infrastructure, because as far as we know, nobody on the market today actually bends sheet metal that holds 20 GPUs in addition to 20 networking cards, all inside of a single compute element. And when we're talking about disaggregated infrastructure, we're not forced to put all of that stuff inside of a single box. So I'm going to kind of keep moving forward here because I do want to leave a few minutes for questions. Usability is a big piece of what we do here. So not only do we have to have, dynamic configurable pools of disaggregated hardware, but we have to make all of this stuff actually very usable. So one of the things that LIQID spends a lot of our energy doing, number one, is being able to support multiple fabric types. So whether we want to disaggregate over Ethernet, over InfiniBand, over PCIe, soon we're going to be disaggregating over something called CXL. It doesn't matter. A single piece of software should be able to manage all of those physical interconnects. The second thing that we do is we manage all device types. You can't be a truly disaggregated composable solution until we're addressing all of the elements: storage, GPUs, FPGAs, networking cards, memory. All the components need to be disaggregated. And then the third thing that we focus on is making all of this stuff usable. There's a lot of existing orchestration frameworks that exist inside the data center today. Our job is not to go off and go build a better orchestration stack, go build a better Terraform, go build a better Slurm, go build a bit better, a Kubernetes engine. That's not the point here. The point here is to be able to integrate with all of the existing frameworks that our customers are using today and make this infrastructure run even better by leveraging the tools and frameworks that are popular in our customers' environments. So I'm going to jump here for a second because I do want to make sure that we cover MX, because that was the topic at hand here. Sorry, let me find the right slide. So we've been working with the Dell team to add disaggregated capability to the MX7000 platform. The Dell MX7000 is, a modular infrastructure solution from Dell, where we have up to 8 blade chassis inside of a 7RU solution. One of the challenges is that being able to deploy GPUs inside of a blade server is actually very difficult. So what we've done is we've partnered with the Dell team and we've disaggregated the GPUs into a standalone pool of resources. So we can deploy up to 20 full-size GPUs, FPGAs, TPUs. It doesn't matter what the device type is. 20 full-size devices into a standalone expansion pool, and then leveraging a PCIe fabric, we're able to connect that expansion pool to the nodes of the MX7000, and then leveraging our software, we're able to slice off resources from this expansion pool, compose them over to these compute nodes. And as far as the compute nodes are concerned, those devices are plugged directly into the motherboard of the compute element. The application layer running on these compute elements is not able to tell that we are pulling those resources from a standalone pool of devices. So very excited about this offering. Today, we're doing Gen 3 composability over PCIe. We're actively working on Gen 4 also. We expect to launch that here in the very near future. The expansion drawer that we are using in this solution is a 7RU chassis. And to this 7RU chassis, we can deploy up to 20 full-size devices. There are by 16 connections. We can do double wide, double width, whether it's a GPU, an FPGA, an NVMe device, a DPU, it doesn't matter to us. We give expansion capability to the MX7000. A very straightforward design. It's literally a single cable that connects our expansion pool over to these compute elements, and then these compute elements can begin to leverage the devices in that disaggregated pool. We have scale out architectures based around this. So not only can we do this for a single chassis, we can do it in multiple chassis environments. And there's several advantages to kind of taking this disaggregated approach of adding GPUs to the MX in a disaggregated pool. Number one, it's scalable, right? So not only can we add 20 of these devices, we can actually add 20 of these devices to a single compute node. So if you have an application that requires absolutely the highest levels of performance, we can build scale up environments where we can deliver, kind of next generation of performance. It's a shareable resource. So meaning that I can give a certain amount of these accelerators to compute number one, and then over time, if that compute doesn't need them, I can move them around to different compute elements inside the chassis or inside the rack. It's dynamically reconfigurable in the sense that when we say we can move GPUs around, you don't actually have to even power the server off to be able to do these things, we actually support device hot plug. So I can have running compute elements and I can hot plug devices into running compute elements, and I can do it in real time without ever powering anything off. It's a disaggregated architecture in the sense that if I need to go off at any point in time and service the accelerators that are in this expansion pool, I can do that without disrupting my application, in the sense that I can leave my servers up and running. I can power down the expansion elements. I can service that pool of resources without bringing down the entire server. We support advanced features like peer-to-peer, which we don't have enough time to cover today. And when we support next generation devices. So as NVIDIA begins to release things like A100 and beyond, this platform is already enabled to go off and do that. And for those that want to learn more, happy to share the performance data, but we do have a large set of performance data that we have measured on this platform. And so not only are we able to scale up to 4 and 8, in some cases 16 GPUs, we can do it with the level of performance that our customers would want. So with 2 minutes remaining, Luis, I will pause and see if there's any questions from.
Yes, we have a couple of questions on, thank you for your talk first, and we have a couple of questions on the Slack. The first question is from Blake Willis. He says, do you have an idea of the maximum length of a passive PCIe 4 copper cable between host and switch?
About 3 meters.
Okay, next question is from the Basis Vera. How large is the disaggregated composable system be? Rack level, multiple racks, whole data center?
If we're doing it over PCIe, the answer is a few racks of infrastructure is what we can disaggregate and compose. When we're doing it over Ethernet, we can go data center scale.
Blake Willis has another question. Are you taking advantage of the PCIe switching features like NTB built in to modern radix, high radix server CPUs?
And so that's a much deeper discussion that probably doesn't get answered in 1 minute, but the answer is yes, we have full control over the PCIe switching fabric and take advantage of things like non-transparent bridging, for sure.
Silei Zhang asks, is there a scalability issue with using native PCIe fabric versus high-speed Ethernet switching?
Yeah, so the scale limit on PCIe-based composability is a few racks of infrastructure. So think each hop is about 3 meters. And so no more than 2 to 3 racks of infrastructure is what we would disaggregate leveraging PCIe. The way we do it in large deployments is we have multiple pods. You can have 3 racks of infrastructure be a pod, but have 10 pods of infrastructure inside the data center. If we want to compose at scale, it must be done over Ethernet or InfiniBand.
Another question from CC Yuan is, can you talk about power break feature?
Yeah, so power, there's lots of advantages related to power when you begin to disaggregate. The simplest one is our GPUs tend to run 15 degrees cooler than when they're disaggregated versus putting them inside the box, for a simple reason. When we put GPUs inside of a box, we are feeding the GPUs with dirty air that has gone past the storage, past the DRAM, past the compute. When we disaggregate the GPUs into their standalone pool, we're feeding them with fresh, cold, clean air, and our GPUs tend to run about 15 degrees cooler as opposed to being placed in the server. And power is a much deeper discussion. If anybody would like to learn more, please reach out. We're happy to do a deep dive on power, signal integrity, or anything else.
And the last question, since we're running out of time, is what is the total PCIe bandwidth supported between blade chassis and expansion chassis?
It's programmable, right? And so each link on a standard server can be a Gen 4 by 16 link, which provides you 32 gigabytes a second of throughput. And we can do up to 4 links inside of a single server to provide up to 128 gigabytes unidirectional out of a single compute node if that's what we need to do. So it's a very flexible architecture where you can scale up the amount of bandwidth required.
Okay, thank you so much for your presentation, and we're going now to our next speaker.